Okay, we're going to talk about graphs and circles. Um, First, we want to talk about intersects, x-intersects and y-intersects. So intersects, intercept points, and we got two of them, x-intercepts and y-intercepts. It could be that an x-intercept is also a y-intercept. That happens only one time when the intercept is 0, 0. And by the way, we're talking about x-intercept points and y-intercept points, which means they have two coordinates, x and y coordinate. So when we have a graph of anything, how can we detect we have an x or a y, an x or a y intercept? So this point that is on the y-axis, we call it the y-intercept, has the characteristic that the first coordinate is 0. Because in order to go from the origin to here, we don't go to the right or left, we just go up and down, meaning that we have 0 in the direction of the right or the left. And then we have some number. But that is the main characteristic, that we have a 0. So we can pin down where the x or the y-intercept in this case is by setting x equal to 0. So this is the x value. If x is equal to 0, that will take us to what the value of y should be. Similarly here, but not exactly in the same way, the characteristic of the x-intercept is that the y value is 0. So the way we can figure out what the x-intercept is by setting y equal to 0, and that will do. Let's look at some examples of finding the x and the y-intercept. So example 1, say we have y equals 3x squared minus 30x plus 63. And we want to find the x-intercept point and the y-intercept point. There may be more than one x-intercepts. There may be more than one y-intercepts, especially if we don't have a function. It is a function because for every input, there is exactly one output. So there could be more than one x-intercept. Definitely the way this is written, there's only one. If there is any one y-intercept point, or we may have none. So whenever we ask a question, find them, or what are they, it is possible that the answer is none or more than one. Whenever we ask for them, we mean all of them. So whenever we ask find the x-intercepts, we mean find all of them. Anyway, to find, going back to this picture, let's start with the y-intercept. That is the easiest one to do. To find the y-intercept, we set x equal to 0. Okay, so finding y-intercept point. All right, so the way we do that is by setting x to be 0. Why? Because we know that's what the y-intercept would look like. It will have an x value of 0. So we go ahead and do that. We set x to be 0. Here's a relationship between x and y, but we set x to be 0. So y will be 3 times 0 squared minus 30 times 0 plus 63. So that is, of course, 0 times 3, 0 minus 30 times 0, 0 plus 63. Of course, you can do this without writing all of that out. Okay, so the answer will be 0, 63. That is our y-intercept point. Finding the y-intercept point, there it is. Okay, now let's finding x intercept points. Actually, in both of them, I should have put plural because we don't know whether we have 1 point or 2 points or none. We don't know. So set y equal to 0. Why? Because the x-intercepts, if any, will have a y value of 0. So we draw that conclusion from the pictures, from drawing a generic picture. Okay. So then this equation becomes 0. It isn't like it was equal to 0. We are setting y to be 0. So 0 is equal to 3x squared minus 30x plus 63. So we solve this equation for x, which you are quite familiar with. We can divide by 3 on both sides of the equation. Divide by 3. So we end up with 0 equals x squared minus 10x plus 21, which is easily factorable. X minus 7, x minus 3 will do. And you guys know the drill. By the zero product property, each one of those is equal to 0, and consequently x equals 3 or x equals 7. So x equals 3 or x equals 7, but we want to give the x-intercept points. The y-coordinate is 0. That's what we started out here with. So we have 3, 0, and 7, 0 are our two x-intercepts. So this graph has two x-intercepts and one y-intercept. So if we don't take into account the scaling, the graph, let's say we have 2, so 3, 7, and then 63 doesn't quite fit in this, but let's pretend it did. We would have this kind of picture, which is a parabola there. This is a sketch, not a complete graph. Well, it is sort of complete because the behavior of the graph continues being the same way. So the intercepts are very helpful because it tells us the behavior of the graph, especially since we have a quadratic. We know that and if we didn't know before, if you have a quadratic function, we will end up with a parabola. A parabola, of course, is something either looks like that, looks like this, typically, although we could have a parabola that opens to the right or opens to the left. This parabola opens up, parabola opens down. Because of the intercepts, we can tell this parabola opens up. The parabola is symmetric. It has an axis of symmetry. The axis of the parabola goes right through the center. Since the two intercepts are 3 and 7, what is the midpoint between the two? Add 2 to get 5. Take away 2 to go from 7 down to 5. So the midpoint is 5. So that means that the vertical line, x equals 5, is, by the way, the axis of symmetry of the parabola. So we're getting more information. And we started out just with those 3 points, the y-intercept point and the x-intercept point. So we can gather a lot of information about that parabola. This point up here, by the way, would be 63. So that gives us an idea, 0, 63. This is a little misleading. I should put, let me redraw that as 3, 0, and 7, 0. That's better. And this is the origin back here. So we go 3 units there, 4 more units to get to 7. The middle is 5. That is an axis of symmetry. Not all graphs are symmetric. This one is. Second example. Example 2. Say you have y equals negative 5x squared minus 30x minus 45. And we want to find, again, the y and the x intercept points. Well, the y is the easiest way to go. So that's how I start. Because to find the y-intercept, all you have to do is set x equal to 0. Set x equal to 0, comma, so y equals, 0 squared times negative 5, 0. 0 times negative 30, 0. So we have 0 and 0, and then negative 45. So 0, comma, negative 45 is the y-intercept point. Okay, so this is one part of the problem. This is one paragraph. We're finished with that. Now we're going to set, so we start a new bullet if you want to, or a paragraph. We're going to set y to be 0. Okay, so now we have the equation 0 equals negative 5x squared minus 30x minus 45. And of course, I can, or we can see that negative 5 is a factor of each one of those terms. So we can divide, comma, divide by negative 5 to obtain. Now, remember, we have a 0. We set y to be 0. So there was a y prior to starting this step, but now we set the y equal to 0. So now we have 0 equals that. It is very important to distinguish that equation versus this equation. That's a function. That means there's a relationship between x and y. There's a correspondence. Y cannot behave widely. It has to behave relative to how x rules. You know, this says square the input, multiply by negative 5, and so forth. That's how y has to behave. Here, there's no y involved. I guess artificially, we could just think of that as a y value. Coming back to this, that's another way to think of it. But we're thinking of this as an equation that is fixed at 0. And we're finding the x values that cause this equation to be a true statement. You know, if you just plug in any number like 0 for x, we're not going to get 0 out. We're going to get negative 45. That's what we did here. So not every number will work here, and we got to find exactly the numbers that will work. Anyway, let's divide by negative 5. So we end up with 0 equaling x squared plus 6x plus 9. Okay, that's an interesting one, because then we have 0 equals x plus 3 times x plus 3. So by the zero product principle, x equals negative 3 or x equals negative 3, but they're the same thing. So there's only one solution to this equation, x equals negative 3. And that means there is only one x-intercept. So the only one, whoops, let me scratch that, x-intercept point is negative 3, 0. So this is the only one. And did we write down? Yeah, there it is. 0, negative 45 is the only y-intercept and only one x-intercept. Now, let's draw a picture of this. That means that, okay, so the x-intercept is negative 3, 0, and that's the only one. The y-intercept is negative 45. Well, that is interesting. So there's a parabola. I can tell that it is opening down. We will analyze this in more detail as we get into parabolas, fully into parabolas. Right now, we're just talking about x-intercepts and y-intercepts, but might just as well talk about parabolas as long as we are solving those equations. So this guy is negative 3, 0. And again, this is not proportionally correct. And then we have a point down here, again, not proportionally correct, 0, negative 45. And it's okay to do non-proportionally correct pictures because we want a sketch, not a perfect graph. But the sketch yet has to be accurate, has to have correct information, accurate information about the behavior of the graph. So this parabola opens down. The y-intercept is 0, negative 45. The only x-intercept is negative 3, 0, which means that it doesn't go past the x-axis. It gets stuck at the x-axis. The parabola goes up to the x-axis and then touches it at the point -3, 0, and then it comes back down. So it is a parabola opening down with one x-intercept and with one y-intercept. Parabolas, generally speaking, have always one y-intercept because there's going to be a point, whether they open up or down, where they will cross. Actually, vertical parabolas. Vertical parabolas are the ones that open up or down. They will invariably have a y-intercept. X-intercept, they may have one, or they may have two, or they may have none. So that varies depending on the individual particular parabola. Okay, so there's our example 2. There are some examples that, of course, are not parabolas. Let's consider this example 3. 3x plus 4y equals 60. Okay, so now we got a line. In order to find the y-intercept, we set x equal to 0. Set x equal to 0, comma. So 3 times 0 is 0. So we just are adding 0 to 4y. That's going to give us 4y equals 60, which means that y has to be 15. So the y-intercept point is 0, 15. Okay, so that's one thing. We're finished with that idea. Now let's move on to a second idea. We're going to set y to be 0 within the same problem. So set y to be 0. So, okay, so if y is 0, 3x equals 60. Or x has to be 20. Okay. The x-intercept point is 20, 0. 0 because that's how we started. We set y to be 0. And that forces x to be 20. If we set x to be 0, that forces y to be 15. So there's the one y-intercept and the one x-intercept. Let's go by fives. So 5, 10, 15, 20. That's the point 20, 0, 5, 10, 15. And if we draw the line crossing those two points, there. We know we have a straight line, and this is a pretty good picture. Again, we have to take into account this is 20, not 4. So each one of those is 5, 10, 15. So 20, 0, and then 5, 10, and then this point will be 0, 15. So there we have a nice graph just by looking at the x and the y-intercept. So they're valuable. They're good pieces of information about the graph. Example 4. How about y equals x minus 2, x plus 1, x minus 9. That's a 9. Okay, so we set x to be 0. So y will be 0 minus 2, negative 2. 0 plus 1, 1. 0 minus 9, negative 9. And when we multiply all of that out, we end up with positive 18. Consequently, the y-intercept is 0, 18. The y-intercept point is 0, 18. Okay. Now, independently, we're going to find the x-intercepts. So now we said y equal to 0. So that guy, 0, is equal to x minus 2, x plus 1, x minus 9. So please notice the difference between that and that. That's a function of x, and it is labeled as y, called y. And this is not a function of x, as is, it is an equation. So please notice the two. So there's an equation function, and if we didn't have the equal, we wouldn't even have an equation. That would be an expression. Please, please, please. In fact, I'm going to emphasize that in a moment. So by the zero product principle, there are three solutions: -1, 2, and 9. So x could be -1 or 2 or 9. And so there are three x-intercepts. The x-intercept points are a -1, 0, 2, 0, 9, 0. So there we have the x-intercepts, a single y-intercept. So what does that mean? -1. The graph looks like this, and then 2, and then 9. It sort of looks like this. So here we have -1, 0. Now, we don't have enough information yet to figure out whether the graph is going up, whether we hit the y-axis on the way up, or on the way down, or right on top. We don't know that. So the only thing we know is that we are crossing the y-axis at 0.18. Right there. That's the only thing we know. We do not know whether we're hitting that on the way up or on the way down or in the middle. This point we do know is 2.0, and this point is 9.0. Again, we haven't gone over why this is the shape of that graph. Polynomial functions kind of wiggle like that, but we haven't done polynomial functions in full detail. Right now, the only thing I'm emphasizing is we have 3 x-intercepts, 1 y-intercept. So because we haven't gone over polynomial functions, this could be thought as a guess of how the graph would look like. Okay, let me just make sure I count the examples correctly. 3, example 4. Let's do one more. Example 5. Say you have y equals x minus 3 times x plus 7 plus 9. That's it. I was going to put equal to 0, but then that would be not good. Okay. So to find the y-intercept, we set x to be 0. So y is equal to 0 minus 3, -3. 0 plus 7, 7. But then on top of that, we're going to add 9. Notice that we are multiplying those two. That is -21 plus 9. And that's going to be -12. Let's just equals -12. So the y-intercept point is 0, -12. There. Okay. How about the x-intercept point or points? We set y to be 0, comma. So 0 is equal to x minus 3, x plus 7, plus 9. We can move the 9 over. Can we? Not really. Well, we could, but that won't help. Because, see, I'm getting a little confused. I'm not. That's just, but this may seem confusing at first because we're thinking, hey, isn't the answer 3 and -7? No, we don't have a product that equals 0. We have a product plus 9 that equals 0. So we cannot use the zero product property on this equation. So first, let me emphasize that. We cannot use zero product property because we do not have a product. And we have to have a product. That is why it is called the product, this zero product property. Now, somebody could say, well, what if we write x minus 3, x plus 7 equal to -9? What if we move the -9 over and we just rewrite it the other way? Can we say that x equals 3 and x equals negative? No, because we don't have a 0. And then somebody may say, well, what about x minus 3 equals -9? But then we don't have a 0 again. We cannot use that property. So in this case, we don't have 0. So no. Can we solve it that way? No. And that is a really good problem that I like to put in tests where we have a product and then we may be thinking, oh, so I just use this zero product property. And then if it is not equal to 0, some students may be thinking, well, we're just going to say x minus 3. So let me tell you what not to do. What not to do. There's many things not to do. But one of the things we cannot do is say, oh, x minus 3 equals -9 and x plus 7 equals -9. That would be really, really bad. Don't do that. Yeah, the only time we can split up and make it equal to 0 is if we have a 0 product. Otherwise, we cannot. So no. Okay, so what do we do instead? All right, I'm going to copy the original equation with a 0 in it. So x minus 3 times x plus 7 plus 9. Well, just multiply this out. FOIL that out. So we have x squared plus 7x minus 3x. I'm going to do 4x at once, minus 21 plus 9. So that is equal to x squared plus 4x minus 12. So those two combine to make the -12, which in turn can be factored. Whoops, I didn't mean x squared. I meant x minus 6 times x plus 2. Let's see. Nope, because that is going to give us -4x when we FOIL back. So it's got to be x minus 2 and x plus 6. That's because 6 minus 2 equals the 4. Now we have a 0 product. 0 product. And all of that is equal to 0. So 0 product. So now we can use, the zero product property, ZPP, zero product property. And that says that x plus 6 is equal to 0 or x minus 2 is equal to 0. So x equals -6 or x equals 2. But let's remember what we are after. We're after the x-intercepts. So the x-intercepts will be -6, 0, and 2, 0. So here are our x-intercepts. Here is our y-intercept. This is a disguised quadratic. X times x is x squared, and there's no higher x that is going to show up in this polynomial after we FOIL it out. In fact, there it is. So had we not changed that into 0, kept it as a y, we would have y equals x squared plus 4x minus 12. which is similar to the one of the problems we did earlier in this video. And so we would know this is a parabola opening up, although we haven't gone into parabolas in full detail, but I can advance to you that if there is no negative number in front of the x squared, then we have a parabola opening up, and we have the two intercepts in addition to the y-intercept. So we can even draw a picture of the parabola. Okay, so 2, 1, 2, and then 1, 2, 3, 4, 5, 6. And then I have to change the scale on the y's, otherwise I won't be able to fit my negative 12 in this picture. So pretend that is negative 12. Now, parabolas are symmetric. Vertical parabolas are symmetric. So that means that the center of the parabola, or the axis of symmetry, is going to be between negative 6 and 2. So that is at negative 2. So here's where we have the center of symmetry. And so the center, or the bottom of the parabola, is going to be at that negative 2. So we're going to hit the y-axis on our way up. And the parabola continues in both ways. So this point is 2, 0. This one is negative 6, 0. This point, well, the axis of symmetry is x equals negative 2. And the only reason why I know that is because I was trying to figure out the middle between 2 and negative 6. So I bulleted it and I checked, 4 over this way, 4 over this way. Yep, that's the middle. So that's how I know that. Oh, and the y-intercept is 0, negative 12. Of course, this is not, the scale of the y is not the same as the scale of the x's, because it doesn't make sense that this distance is 2 and then this distance is 12. Even if it's negative, it doesn't make sense if we were using the same units horizontally as vertically. So these are good examples of x and y intercepts, if I may say so. As we are learning more about functions, we have to get to know functions very, very well. So the following ones are well-known functions. So there are some functions that are good examples of many things, and so it's best to become familiar with them. I'm trying to think in biology, there are some mammals that lay eggs, and that is a good example to know, because otherwise we may be thinking that all mammals give birth by other means than eggs. So there are some examples that we have to know, because either they're very important, like dolphins are mammals, but yet they are in the water. So that is a good example that tells us, whales are mammals that are well known. And so we cannot just generalize, so all mammals have to be land animals, and that's not true. Dolphins and whales are mammals. So again, I'm beginning to talk about things that I do not know too much about. So the point I'm trying to make is that there is a lot of examples we have to know really well, in general, in mathematics, in biology, in chemistry. I'm sure every topic, discipline has important examples that we should know very well. So as far as a function goes, let's label this as example 6. Again, I want to make sure my numbers are correct. Yeah, last example was 5. So example 6, y equals absolute value of x. And we're going to milk this even more in future videos, especially when we start shifting and changing and transforming functions. So this is a well-known function. Make sure you know it. It is a line that starts, a ray that starts on the origin, and another ray connected to this one that also starts on the origin. And they're 45-degree angle relative to the x-axis and the y-axis if the units are the same. So many functions are smooth. They don't have sharp corners as this one. This one is one of the ones that have sharp corners. So the thing to notice with this, which is really cool, I think, is, okay, so is this. I can show you what the absolute value does to anything. Let's say you have y equals x, which is not the same. Those are not the same, okay? This graph looks like this. Everybody should be familiar with this, a slope of 1, just a straight line through the origin. Now, if you put an absolute value, anything that is under the x-axis will fold over the x-axis. And that's what happens here. So this graph sort of starts with this graph, and when we put the absolute value, all that is doing is literally folding this, pretend I'm folding the page over. So this line, which used to be down here, gets flipped over and now becomes this one. Let me give you another example, 7, which is not part of this class. It isn't. But I just want to show you how dramatic this is. Let's say you have y equals sine of x. Don't get scared. Uh, this is a wave. I'm just going to tell you what it looks like. It looks like this. So it's a plane wave, and it just cycles over. And on the left, it does the same thing. I just don't want to draw more on the left. But that's a wave, and I don't need to go beyond this. So this is sine of x. Just keep that in mind. It is a wave, and it's periodic. It just continues doing the same thing over and over again on the right as well as on the left with the same kind of pattern. You're thinking, well, what does that have anything to do with the example? Well, if we were to, so this is one example. If we were to do, let's label it as A and B to distinguish it. If we were to impose an absolute value on it, and you knew how this looked like, all you have to do is everything that is under the x-axis will be flipped over. So this bump stays as is. I'm going to try to keep the same. All right, this one that is under flips over, just like this piece of line, this segment got turned over here. So this one that is under now goes over the line. This one is already over, keep it. So anything that is over, keep it. Anything that is under, flip it. Over, keep it. So we end up with bumps with sharp corners as we connect them. And that is the function of y equals the absolute value of sine of x. So if you put absolute value, pretend there isn't, and you want to know how it looks like, pretend there is an absolute value, draw the picture the way you know it, and then flip whatever is under the x-axis. Hey, let's do that with a parabola. This can be actually fun. Where's a picture? Okay, back to example 1. So I'm going to make a new example out of this. Example 8. Yeah. If we have y equals 3x squared minus 30x plus 63. Remember this? This was our example 1. And when we did it, we said, oh, the parabola goes through 3 and 7. I'm going to focus on that, 3 and 7. So this, we already did this, and the parabola goes like that, okay? And this point is 3, and this point is 7. 3, 0, 7, 0. Okay, there. This is just, we did this in example 1. Now, let's label this as A. As a second example, if you had the same thing, but put a big absolute value around it, 3x squared minus 30x plus 63, close the absolute value. And you wanted to draw this picture, if you already know this picture, piece of cake. All you have to do is go down the same way. This piece that is under the x-axis, flip it over, and then continue. Isn't that cool? So this is still 3, 0. This point is still 7, 0. This point would be the same one, 63, but I don't want to focus on that. I want to focus on those two. So if this is positive, leave it alone. This portion is negative, flip it over, and then keep the positive the same way. So absolute value is not that intimidating once we know that we have to flip things over. It's actually fun. Example 9. So that was the absolute value function. I'm not necessarily going to go through each one of those um, in that much detail. Y equals square root of x. An important function to know. This is pretty much a parabola, except that it is not a full parabola. It is half a parabola. It starts with 0, 0, and then 1, 1, and then 4, 2, and then 9, 3. And so it looks like that. Starts there and doesn't end, and it is curvy. It curves while it is going up. Okay, so that is y equals square root of x. Not to be confused, let's make an example out of this with y squared equals x. Those two are very different. Please do not confuse them. It's easy to confuse. This one has that and has a negative to it. So this one as is means the principal root, which means just the positive one. When we are solving this equation for y, we're going to end up with plus minus the square root, plus minus, plus minus, plus minus. So we have actually two parts to it, while this one only has one. Very, very easy to confuse the two of them. This is not a function. Why not? Because for every input, there are two outputs, the positive and the negative. This is a function because for every input, there is an output. So for instance, 1 point here is going to be 9, 3, while the point directly below will be 9, negative 3 on the same graph. This one only will have 9, 3 without 9, negative 3 because this is the principal root. It's very, very easy to confuse one with the other because somebody would say, well, square that on both sides of the equation and you get this. Yes, remember, every time we square a variable, some strenuous solutions may be filtering in. And that means that they're not the same. In this case, they're not the same. So be aware of the two. This one has symmetry. The symmetry would be the horizontal line. This one has no symmetry. We will talk about symmetry in a different video. There's a lot to talk about when we are dealing with symmetry. Let me give you a preview about symmetry, though, before we start talking about circles. The term symmetry is relative. Relative to what? Yeah. Yeah. Symmetry is not absolute in the sense that there's no one kind of, there's many kinds of symmetries. That's what I was trying to say. So pretend you got a butterfly kind of picture, and a lot of us think of a butterfly, if it's a perfect butterfly without missing any part to it. Butterflies are pretty symmetric, or we think of them as symmetric. And by that, what we mean is that every point on one side of the butterfly will have a corresponding point across the axis of symmetry. So this point has a friend up here, and this here. So for instance, is the number 5 symmetric? And the answer is no, because if you try to draw a line through the center, this point doesn't have a friend out here. So this is not symmetric. This is symmetric. All right. So that is symmetry across a vertical line, but there could be a symmetry across a horizontal line. There could be a symmetry across a diagonal line. And you may be thinking, well, that's kind of the same thing. Yes, in addition to that, we have symmetry across a point. So let's say you have an S, a perfect S like this one. This is not symmetric with respect to any line. However, it is symmetric with respect to this point in the following sense. This point has a corresponding pair opposite, and this point has a pair opposite to the point in question at the same distance, and so forth. So every point has a point that corresponds to the original point across this center of symmetry. So we can have symmetry with respect to a line or symmetry with respect to a point. So is an S symmetric? Depends. With respect to a line? No. With respect to a point? Yes. So just be aware there is different kinds of symmetry, and we have to keep an eye on that. Yeah. Now let's talk about circles. How do we know we have a circle? A circle has a center, and the property of circles is that no matter which direction you go, if you go in this direction or you go in this direction, boy, that looks like a clock, or if you go in this direction, it doesn't matter which direction you go into, or if you go in this direction. The distances, all of them are supposed to be perfectly exactly the same. So the distance to here, those of course are called the radius of the circle. There is only one distance. It's supposed to be perfectly exactly. So when I'm drawing this picture, initially it did look pretty circular, but now that I'm drawing a center, I can tell this side is a little longer than this. So my picture is not perfect, of course. Had it been perfect, and had I found the perfect center, then all of those distances would be spokes of exactly the same length. It doesn't matter which way you put a spoke, it will go exactly the same distance. If we are short or longer than any other spoke rather, that means that the picture is not a circle. It may look like a circle, but it's not a circle. All right. So how do we find the distance between? Let's assume that for now, let's assume that the circle has center at the origin. So center at origin. So let's pretend we have a generic point x comma y, a center 0, 0, and the distance has to be fixed. And we're going to label the distance as r for radius. And we're going to assume that the distance is fixed. Well, we have a distance formula between the origin and a point. Remember that? It was the distance, in which we're going to label r, is the square root of x squared plus y squared. If we are measuring the distance from the origin, if we square both sides of this equation and then just move them around, we end up with x squared plus y squared equals r squared. And this is the equation of a circle with center at the origin. Mind, center at the origin. Many circles don't have centers at the origin. They have centers somewhere else. Let's say we have a center at 2, 3. Okay, so I did not want to make this an example, but let's start with examples. Example 11. If we want to have a circle of radius 2 with center at, say, we'll start with something like 2, 3. All right. So we go 1, 2, 1, 2, 3. That would be the center of our circle, and it will go because that's the center and the radius is 2, it will go 2 units to the right, 2 units down, 2 units up, well, 2 units in every direction diagonally, and we end up with this. Actually, this point will be in contact with the y-axis. It won't be in contact with the x-axis. The circle won't be because it is 3 units off. But what is the equation? The equation is really x minus 2 squared. So that is what we label as a shift to the right from the origin, plus y minus 3 squared equals the radius squared, but the radius is 2, so that is a 4. X minus 2 squared plus y minus 3 squared equals 4. Oh, the question is, why do we subtract the 2 and the 3? Remember our shift, yeah, our shift from the origin to here, it was done by subtracting the point. Yeah. So if we wanted to shift this distance down to here, what we need to do is subtract the 2 and the 3 correspondingly. So this distance we want it to be 4. This distance we want it to be 4. All the distances we want it to be 4. But we know how to measure distances from the origin. So the way to handle that is to anchor the origin down to here. But the way to do that is by subtracting the number. Now mind, if the center had a negative coordinate, then when we subtract a negative coordinate, we end up adding a number, a positive number. Okay, so the center of the circle is 2, 3. One of the things that we are going to be doing in this class, is, well, actually, let me do something else, and then I'll tell you one of the things we're going to be doing in this class. Fold that out and simplify. So this is the equation. Okay, there it is. But I want to do more with it. Let's do a little bit of algebra. FOIL this out, so we end up with x squared minus 4x plus 4. That is the x minus 2 quantity squared. And then FOILing this out gives us y squared minus 6y plus 9, still equal to 4. And let's move everything to the left side of the equation. So we have x squared, and rearrange things. X squared and y squared minus 4x. I'm going to underline the ones that we already wrote down, minus 6y. And here's the thing. We have a bunch of constants. 4, 9, that is 13. But then when we move this 4 to the other side, those two 4s actually cancel off. So we end up with 9 equal to 0. This is another way to write the equation of the circle. The same circle, because all we did is expand and add it together, all the parts of those squares. So this is the same circle. One of the things we're going to be doing in this class is to be able to go from here to here. So in some problems, you will start with this, and you have to end up with the correct equation. So the question is, how do we recoup this original equation if you start with that? And we do that by completing the square. Okay, let's do an example where we actually do that. Example 12. Let's say we have x squared plus y squared. We always start with those two. Minus 8x plus 10y. I'm going to make this up, so I don't know if the radius is going to be a nice radius or not. There it is. Okay, so one of the questions I'm very likely to ask you in tests is start with this. This is the kind of question. Figure out the center of the circle. This is going to be a circle, and the radius. So the way we go about that is to go back to this form of the equation of the circle, and that will directly tell us the center and the radius. And we do that by completing the square. So this is the way I go about it. Put the x's together, x squared minus 8x, and build a little bit of space to complete the square. Plus, do the same thing with the y's, y squared plus 10y, build a little bit of space to complete the square. The equation, I'm running out of space here. I'm going to move this, so I'm going to put the rest of the equation here. So equals 7. Okay. So I did not change the equation yet. Well, what I mean by that, I did not add or subtract anything. The x squared is there. All the parts are just in the same, we have the same parts just placed differently. So x squared, the y squared is here, the negative 8x is with the x squared, the 10y is here, the 7 got over, so we added 7 to both sides of the equation. I guess we did add 7. But what I mean by that is we did not add other things, anything else other than the parts that are already there, or subtracted anything other than the parts that are already there. Okay, so remember how we complete the square? Half the negative 8, square it, and that's the number that goes here. So that is going to be 16. Negative 4 squared is 16. Same thing there. I'm going to bump into the 7 if I draw my picture, but let me do it over here. Take the 10, half it, square it, and put it there. So that is going to be 25. Now we cannot arbitrarily just add 16 and 25 on one side of the equation without doing the same thing on the other side of the equation. So equals 7 plus 16 plus 25. This equation should, well, ideally it should fit in one line. You know, we got this polynomial with only y's and numbers, and then just the numbers. It didn't fit in one line, but that's okay. We know that this equal means that the equation continues underneath. Okay, let's factor this. By this sign, this is going to be a perfect square. It is going to be x minus 4 quantity squared. Plus, again, by design, this is going to be y plus 5 quantity squared. And then we just add the numbers, 25 and 16 and 7. That is going to be 23, 48. Okay. So the center, so there is the equation. For lack of a better name right now, I'm going to call this form the form x minus h squared plus y minus k squared equals r squared. So I'm going to call this the form of that equation. You may be thinking, wait a minute, you didn't, here it says minus and here it says plus. Well, in that case, we're assuming that k is negative, and then we would have a double negative. Anyway, the center, once you have that, the center will be located at the point 4, negative 5, and the radius is square root of 48. But before I do the square root of 48, I want to simplify it. Square root of 48 is square root of 16 times 3, 6 times 3, 18, we carry, yep, which is square root of 16 square root 3, which is 4 root 3. So the radius is 4 root 3. So there we have the center and the radius. Whoa, it's not, in my opinion, this is not trivial. Let's do another example. 13, again, we're going to ask for the center and the radius of a circle. Say you have x squared plus y squared minus 8x plus 9y minus 10 equal to 0. And you may be thinking, oh, I know how to do this. Well, there's a complication in this problem. And that's why I wanted to address this problem. So based on the previous example, keep the x's together. In fact, I purposely use the same negative 8x. That's not the complication. You see negative. So we know we're going to add 16. The complication is on the other trinomial. Y squared plus 9y, add a space, equals, we're going to add 10 to both sides of the equation. We know we're going to add 16 here. We did that here in the previous example. So that's the same thing. Here's the complication. 9. Half of 9 is 9 halves. Square that, and we're going to end up with 81 over 4. So we need to add 81 over 4. So this, I'm running out of space here. Yeah. So we need to add 81 over 4, which is a fraction. That is the complication. The complication also happens here when we factor. Here there's no big complication. We have x minus 4, quantity squared, plus y plus, remember, the number is the one before we square, 9 over 2 squared, equals, that is 26. But we want to add the 26 to 81 fourths. So the 26, 10 and 16 is 26. So we really want to change that into fourths. And that will be 26 times 4 is 104. 104 over 4. That comes from the 26 plus still 81 over 4. So that is really 185 over 4. Okay, so the center of this circle is at 4 comma negative 9 halves. Watch out for that. And the radius is 185. I want to see if I can factor that out into a perfect square. I know 5 goes into 185. So 185 divided by 5, 37. That is a prime number. So that means we cannot simplify the 185 when we root it. So the radius is square root of 185, but the denominator certainly can be square rooted, and that is 2. Yep. So the radius is square root of 185 over 2. The center is located there. All right, and with this, we finish this video.